Only 26 students are there. Please send the WhatsApp message in your group to join the class, all the students.
Yes, sir.
Okay, are you able to see the slides?
Yes, sir.
Okay, thank you. Yeah, just what we discussed in the last class, just a recap, first 2 minutes, then we go for the problem discussion today. And already I have shared the slides. I mean, what are the problems there in the slides? Today we discuss further few more problems. I will take it from some other books, and we will discuss tomorrow. I mean, in the next class also, half of the class we discuss this problem. Then we go for the third chapter. Okay, that's what my planning now. So now, yesterday in the last class we discussed the different types of theory of elastic failure. I mean, we discussed the major discussion, major theories like maximum normal stress theory and principal stress theory, only applicable for the brittle material. It's also called Rankine theory. Okay, I mean, here the sigma 1 is equal to critical stress divided by a factor of safety. Our design stress must be 1 minute. Yeah. Our design stress sigma 1 must be equal to sigma critical divided by Fs, factor of safety. We are applying the factor of safety. Suppose if we are not applying the factor of safety, if I put the sigma 1 greater than or equal to critical, then it will be a failure. Okay. When you apply the factor of safety, obviously sigma 1 going to be less than the actual standard condition of the actual standard testing specimen of the stress sigma critical. It's obtained from simple tension test. Right. The second theory we discussed, maximum shear stress theory. I mean the first theory, maximum normal stress theory. This is the equation. This is the diagram. This is the diagram. This is the region of interest. Our sigma and tau, should be within the region. The sigma and tau coordinates, the value within the region, then the component design going to be in safe limit. Suppose our sigma and tau is away from the region, this region, and then it will be a failure region. Hence, we would like to design our component, whatever sigma and tau should be lying within this region. This is the plot developed with the help of the Rankine's theory. Then this is the square. Now I come to this maximum shear stress theory, hexagon. In this hexagon, see here, this first quadrant and the third quadrant are symmetric, and second and fourth quadrant symmetric. And here, that this theory is eligible, suitable for ductile material. And see here that tau 1 2. Tau 1 2 is nothing but tau maximum. Shear stress maximum is equal to 0.5 times of SYT. It's yield distance. Yield distance, whatever we are saying here, sigma critical. We are saying yield distance, 0.5 times of yield distance. Okay. Now this is the hexagon shape, and I come to this maximum distortion energy theory. It's a cubic shape. In this cubic shape, because we derived it yesterday, We have briefly derived it in this concept, and sigma 1 squared minus sigma 1, sigma 2 plus sigma 2 squared is equal to SYT squared. I mean, this is a cubic equation. It's nothing but x squared minus xy plus xy squared is equal to some constant. Then we discussed this cubic form in the von Mises theory or maximum distortion energy theory. Here, the tau 12 maximum shear stress is limited to 0.577 times of sigma YT. I mean SYT, yield strength of this material. This theory is suitable for ductile material. I mean that max von Mises theory and principal shear stress theory suitable for ductile material. I mean, mostly for design purpose, we are considering the von Mises theory. Von Mises theory is, it's little complicated analysis, but this is a better than other two theories. Okay, von Mises theory, and sometimes people are considering maximum principal shear stress theory also. Maximum shear stress theory also they are considering. Now, this is a comparison between all these theories. I mean, the first one is maximum normal stress theory. The second one is maximum shear stress theory. The third one is cubic theory. Now, based on this problem, we are going to discuss. Another theory. There are maximum principal strain theory and maximum strain energy theory. I mean, these two things you can easily understand. If you are understanding these three theories, you can easily understand these two theories. Okay, mostly we are going to concentrate these theories only. Okay, I mean, see the formula. Just see the derivation here. Just see the formula here. Maximum strain energy theory: sigma 1 squared plus sigma 2 squared minus 2 mu sigma 1 sigma 2 greater than equal to sigma critical squared divided by FOS, factor of safety. This is a maximum strain energy theory. Just keep this formula in your mind. That it will be, while solving the problem, it will be very easy. Okay. Now, maximum principal strain theory. I mean, sigma 1 minus mu into sigma 2 is equal to sigma critical divided by FOS. How to remember this? Remember this formula. Just first, this formula is very easy. Sigma 1 is equal to sigma critical divided by FOS, maximum normal stress theory. But when you are coming to maximum shear stress theory, based on the Mohr circle, we can easily recollect the information sigma 1 minus sigma 2 divided by 2. Okay. Based on that, right hand side going to come sigma critical. That if once you keep in mind, then you can easily derive it. I mean, when you are coming to maximum principal strain theory, I mean, just you put sigma 1 minus mu of sigma 2. That's all. You are getting maximum strain energy theory. And similarly, first you understand this maximum distortion energy theory. This theory you can easily rewrite it. Maximum strain energy theory. See here, maximum distortion theory we discussed, right? Sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square. I mean, greater than or equal to sigma critical divided by Fs. Critical square divided by Fs. But if you understand this theory, this equation you can rewrite easily. Sigma 1 squared plus sigma 2 squared same. Only here, sigma 1, sigma 2, in that place you have to add to 2 mu. 2 mu, wherever strain is playing, obviously Poisson ratio is going to play important role. So that one you have to keep in mind. Now we move to the problem. See the first problem. 1 minute, I fold my system. Okay, 2 plates subjected to tensile force 50 kilonewton are fixed together by means of the 3 rivets. Here we are using 3 rivets to hold the 2 plates as shown in figure. I mean the plates. Okay. The plates and rivets are made of plain carbon steel 10C4. I mean, this is, we know, right? We already discussed the definition, what this definition representing. With the tensile yield strength 250 Newton per mm square, this is nothing but our SYT. The yield strength of this here is 50% of the tensile yield strength. The yield strength of the shear also they have given 50% of the yield strength. And the factor of safety is at 2.5, neglecting the stress concentration. Okay, now our aim is to determine the diameter of the rivets and the thickness of the plates. Okay. Now, when we are going to find out the diameter of rivets, what is the important role? The rivet is subjected to failure going to happen because of the shear stress in between the two plates. Okay. Then shear stress be very important role for defining the diameter of the rivet. But when you apply the load here in the plates are going to be subjected into tensile load. Hence, the dimension of the plate can be defined with respect to tensile stress. Okay. Now, first we see that the rivet diameter. Then how many rivets are using? They have given clearly 3 rivets are used in the problem in this design, this component. Then rivet 1, rivet 2, rivet 3. Then what is the shear stress area? Shear stress is nothing but a shear load divided by shear load divided by shear area. Right now, they already given shear stress. Shear stress is a 50% of the yield strength they already given. Now, see here. They already given yield strength also given. How much they given? 250 Newton per mm square. Here, people usually they are doing mistake. They are directly taking 250 Newton per mm square into 0.5. Then they will consider as a tau. It's absolutely wrong. When this factor of safety is given, you have to first divide it by factor of safety, your sigma yt. Sigma yt is nothing but syt. Sorry. Okay, syt. Now syt divided by, now the factor of safety is given 250 divided by 2.5. Then after that only you have to multiply with the 0.5% of, then you are getting shear strength. Shear strength is, your shear stress is 15 Newton per mm square. Then direct substitution of the formula. What is this shear stress? Tau is equal to shear stress, tau is equal to force by area. Here shear stress is given. Area pi by 4 d squared. How many rivets are there? 3 rivets are there. 3 into pi by 4 d squared. Load is given already 50 kilonewton. Okay. Then the 50 kilonewton. Then you are able to find out diameter of the rivet here. As I told you that the rivet is subjected to failure, subjected to shear stress. Then we are considering shear stress. Now I come to the tensile stress for plate design. In this plate, the subjected to tensile stress. Tensile stress is nothing but, now we have to take 100 Newton per mm square. We can't take directly this value. Factor of safety is given. Then from this we can find out the thickness of the plate. What is the thickness of the plate? Now see here. Here the tensile stress is nothing but P by A. A is nothing but the projection area. We can't consider this a rivet diameter. Then we have to subtract that. That's what we are considering. 200 minus 3 into d, diameter of the rivet, while considering the area, while evaluating the area. Okay. Into thickness of the plate. Then substitute this formula. Force is given 50 kilonewton. Sigma T is given 100 kilonewton, 100 Newton per mm square. Then only T we would like to find out. Already D is found it. Then we would like to find out only T. Then T can be easily find it from the relation. Okay. Now I come to the second problem. Simple problem only. Whatever we discussed earlier, the basic concept. Even whatever you studied, your strength of material concept is very, very important for solving this problem. The frame of AXA is shown in figure. Shown in figure this, and the initial tension P in the blade should be 300 Newton. Initial blade should be 300 Newton. Okay, 300 Newton, and the frame made of plain carbon steel 30C8. Identification of the material 30C8. Then the tensile strength is 400 Newton per mm square. And factor of safety is 2.5. The cross section of the frame is rectangular with the ratio of the depth and width is 3. Depth width ratio they have given D by W. Okay, D by W ratio is given. Now determine the dimensions of the cross section. Now our aim is to define the dimensions of the cross section. Now the force is acting from the handle. This is handle. We are apply the force here only, right? Then our area of our region of interest here. This is our region of interest. Then the force is applying in the opposite from this region of interest. Obviously, the component going to be subjected into bending stress as well as direct stress. Okay. Now, I mean, the bending stress, whatever bending stress, I mean, what type of stress? Because the force acting inside, right? The force P is acting towards inside. Then, while applying the force acting towards inside, then inner portion going to be compressive stress. The inner portion, the inner portion of the frame is subjected into compressive stress. Okay. First, calculate the permissible tensile stress. What is the permissible tensile stress? They are given yield strength 400 Newton per mm square. They are given factor of safety 2.5. Then 400 divided by 2.5, that is our permissible limit, 160 Newton per mm square. Okay. Now come to the calculate the direct and bending stress. First, calculate the direct stress. Direct stress is nothing but force by area. I mean, the direct stress P by A. You see here, this is XX region. Our interest is this region. What is the dimension? We would like to find out that place. Okay, this region subjected to compressive stress and bending stress. Okay, direct compressive stress P by A. Then load is given 300 Newton divided P by A. I mean, A here T is the cross section is given. T, I mean the depth is given 3T and width is given T. So then substitute here, you are going to get compressive stress. Then what is the bending stress here? We already know the formula. M by I is equal to sigma B by Y. Sorry. Sigma B by Y. From this relation, we are finding the sigma B. Sigma B M by M. Now, M, what is M bending moment? Based on the given figure, you can, based on your component, you have to find out the bending moment. So bending moment here, the load is 300 Newton acting here, and the distance from the region of interest is 200 mm. I mean 300 into 200, and what is this Y? Y is nothing but D by 2. D by 2, depth by 2. This is D by 2. Then 1.5 T. Then what is I? I is equal to B D cube by 12. Then 1 by 12 T into 3 T cube of 3 T cube. Then you are going to get like this in terms of T. Your bending stress is 4000 divided by T cube Newton per mm square. Now, I mean, use the superimposing concept for finding the total stress. Now, here the bending stress, I mean, this is superimposing, then this is in compressive nature, then I am subtracting with this stress, bending stress. This is in compressive nature. Hence, in 40,000 divided by T cube minus 100 divided by T square. Then that must be equal to our permissible limit, permissible tensile stress. Then from these relations, I am able to find out the thickness of the frame, thickness of the hacksaw frame. Once we find out thickness of the frame, we can find it out the, depth of the frame. Depth of the frame is, now I can consider this is 7 mm. Depth of the frame is now, depth of the frame D is equal, this is T is equal to this depth of the frame, T or width. Okay. This is depth is equal to 21 mm. Okay. Now I come to the next problem. A offset link is subjected to a force of 25 kilonewton is this one in figure, is made of gray cast iron. The material is made of gray cast iron. FG300. They have given the grade, notation. Based on that, you can find out the material properties from the table also, if the material properties are not given. Okay. Now, factor of safety is given. Determine the dimensions of the cross section. Now, earlier case, the structure was subjected to compressive load. Now, in this case, what type of stress is subjected? That inner region of the frame. What type of stress is subjected? Anyone, please tell me that. Inner portion of the frame. Inner portion. Tensile. Yeah, tensile. Now, this is the P is outward direction. Hence, tensile load is acting here. 1 minute. Yeah. Now, I mean, this frame is subjected to tensile, direct tensile, and bending moment because our area of interest, our region of interest is offset from the load, right? I mean, 10 mm distance plus t by 2, the depth by 2, right? Hence, we would like to find out how much bending moment is acting in this particular region of interest. Okay, now here also similar, sigma t is equal to SUT divided by FOS. I mean, here they have given ultimate tensile strength, FG 300. FG 300 means the 300 Newton per mm squared, what we discussed in the previous chapter. Okay, then factor of safety is given. This is the limit. This is the sigma t, our designed stress. Okay, now calculate the direct tensile and bending stresses. I mean, see the section, the cross section subjected to direct tensile and bending. This is a direct stress. This is a bending stress. I mean, see, MB is nothing but a bending moment 25 kilonewton into 10 plus T. 10 plus T is, in that sense, we are taking at the middle. Okay, 10 plus T into Y is nothing but D by 2. D by 2 means depth by 2. Here 2T divided by 2, hence T. Okay, then substitute this in the bending moment for finding the bending stress. Then we are finding the bending stress. This is the bending stress component. Okay, this is the direct tensile stress component. Okay, now see here. Now our permissible limit says this is our permissible limit, 100 Newton per mm squared. Now, I mean, this is our component design. This is our component design. Now this is the permissible limit. This value now substitute. I mean, equate both. Then you able to find out T. I mean, this is the third order polynomial equation from this relation, from this expression. Finally, able to find out the thickness of the link. Thickness of the link. Okay. Once you find out the thickness of the link, then 2T you can know. You know that around, I mean, 26 mm, 52 mm. No, okay, these are very simple problem only. Now I come to the next problem. If you have any doubt, please raise your hand, ask me that. Oh, no problem. Okay. The frame of hydraulic press consisting of two identical steel plates. This one, two identical steel plates. Identical steel plates as in figure. I mean, the maximum force P acting on the frame is 20 kilonewton. P here they are given. The maximum for P acting on the 20 kilonewton. Okay, now see here. I mean, the plate made of steel, 45C8. Okay, with the tensile yield strength 380 Newton per mm squared. If the yield strength value is not given, you can go to the table. You can find out corresponding 45C8. You can find out the tensile strength of the material. The factor of safety is given 2.5. Okay, now our aim is to determine the thickness of the plate thickness. Okay, now plate is 20 kilonewton, load is 20 kilonewton, factor of safety given. Then what is the permissible stress limit? I mean, 380 divided by 2.5. This is our permissible stress limit. Now what are the stresses are subjected here while the load is acting? What type of stress is acting here? I mean, the frame is subjected to tensile. The plates are subjected to tensile as well as bending. Tensile as well as bending when the load is acting. I mean, this is a front view. This is from this view. Sorry. Okay, this diagram. Now here you have to see here. This is looks like two plates are there. These two plates are identical and symmetrical dimensions. Hence, obviously, the 20 kilonewton, whatever the 20 kilonewton P is acting here, the 20 kilonewton P is going to be shared here. 10 kilonewton, 10 kilonewton, like that. That's what we are dividing this. 10 kilonewton force here, 10 kilonewton force here, this side. Okay, now we have to find out. Now, because 20 kilonewton given, suppose 50 kilonewton means each side will be set 25 kilonewton, 25 kilonewton. Now, this is whatever we discussed earlier problem, similar. P by A, this is load by area. Load is a 10 kilonewton, and area is nothing but already given T. I mean, here this width is given T. Sorry, that depth is given 150 150 into T. Okay, now we have to find out the bending stress. This is a bending stress formula, sigma B, right? In the sigma B, here load is given 10 kilonewton, and how much distance? 200 plus 150 by 2, 75. We are taking the center, we are taking, at the middle average. Okay, center 200, 10,000 into 200 plus 75. This is nothing but our T. Depth by 2. This D by 2. This is our 75. Okay. Now find out this. I is nothing but BD cube by 12. Then from this you can find out sigma T. Now this is our permissible. This is must be equal to our permissible stress. Then when you are equating this, you are going to find out the thickness of this plate. 5.62 mm. Now I come to the next problem. Okay. Now the cantilever beam of rectangular cross sections used to support the pulley as in figure. This is a cantilever beam supported by the pulley. Okay, supported by the pulley. See here, the tension of the wire is 5 Newton acting here. 5 kilonewton load is acting in the wire. Okay, the beam made of cast iron FG. The beam made of cast iron FG A 200. So 200 Newton per mm square. Okay, yield strength. And the factor of safety is 2.5. The ratio of the depth and width. The ratio of the depth and width is given. 2. The ratio of depth and width is given 2. Okay, now our aim is to determine the cross section dimensions of the beam. Okay, now see, when the load is directly acting in this place, only we can consider only one load, but the load is acting offsetted from the axis of the beam. Okay, obviously the load is offsetted means that away from the axis of the beam. Okay, and this load now not only horizontal, not only vertical load. The beam now subjected into two load components, because the force acting here. Okay, see here, when you are writing this, see, I tell you, yeah. Now this is the load here acting. Now when the wire tension is going to be like this, okay, for maintaining the equilibrium condition, the another force is going to be acting like this. Okay, it should be inner direction. Okay, now you might have got it. This is what the vertical direction load. This is horizontal direction load. Okay, now these are two load components are there in the point in the beam. The structure. Now see here. Now we have to find out the bending moment based on this load, given load. Now how many bending moments going to be there? Anyway, first we see this. You already know. We discussed enough information about the finding the permissible limit stress, right? This is a permissible bending stress, 200 divided by 2.5, because they have given here the beam made of FG8, FG200, and the factor of safety given. Okay, now now see here, what is the bending moment at point A, at point B? We have to find out the bending moment. While finding the bending moment, here horizontal load, vertical load, that this point is acting on the B, then it won't be a vertical moment here. Okay, only horizontal bending moment. 500 Newton into here, 5,000 Newton into what is the distance? 500 mm they have given here. 500 mm they have given here. 500 into 5,000 into 500. That is the bending moment acting. Horizontal force into vertical distance. That is the bending moment acting in the at the point B. But when you consider point A, this is away from the load acting position. Hence, here you can, both the component will be considered for finding the bending moment. I mean, see here, 500 into 5,000 into 500, 5,000 into 500. This is with respect to vertical load, bending moment can be considered at the point A, as well as, because the bending moment, this is away from the 500 mm, okay, offsetting, right? And now the second, and another bending moment, another force, vertical force into this distance. This is very simple only. Distance is, they have given, I mean, 1,500, then 5,000 into 1,500. That's all. So these two bending moments are necessary when you are going to design this, I mean, define this dimension of the beam. Now, draw the bending moment diagram here. At the point A, the bending moment is here 10,000 into 10 power 3 Newton millimeter. Here 2,500 into 10 power 3 Newton millimeter. Now calculate the dimension of the cross section of the bending cross section. The bending moment diagram is shown in figure. See here, this figure. Okay, the cross section of the cross section A is subjected to maximum bending stress. I mean, here the similar formula we are using. These are things d by 2, this is I, this is normal things. Okay, now come to this. I mean, sigma B is equal to mb into I by I. Now see here, which one is maximum bending moment acting in this region, corresponding this region, which one is the maximum bending moment is acting? The maximum bending moment is a 10,000 into 10 power 3 Newton millimeter. So that maximum bending moment we are considering here. That maximum bending moment we are considering here, mb into y is nothing but w, whatever we already discussed here, into w divided by bdq by bdq divided, I mean, here this is a bdq by 12. So this from this, okay, 2 by 3 w power 4. From this relation, this is our permissible limit stress. 80 is our permissible limit stress. 80 is our permissible limit stress. I mean, this is I value, this is y value. Then we are able to find out the, I mean, width of the beam. Width of the beam. Once we know the width of the beam, the depth by width is 2, then we are able to find out the depth of the beam is nothing but is equal to w, then 120 mm. Okay, now I come to the next problem. See here, okay. Now see here, the wall bracket with the rectangular cross section is shown in figure. The depth of the cross section is here 2t. Okay, and twice the width of the twice the width. This is the width of the bracket. Okay, the force P acting on the bracket is a 60-degree angle. I mean, this vertical, the 60 degree to the vertical. I mean, the force P is a 5 kilonewton. Force P is a 5 kilonewton. The material of the bracket is gray cast iron FG 200. Then the yield strength is 200 Newton per mm squared. Okay, and the factor of safety given 3.5. Determine the dimensions of the cross section of the bracket. Assume the maximum normal stress theory. I mean, they have clearly given maximum normal stress theory in this problem. Now come to this problem. I mean, this is, we already know, 200 divided by 3.5. That is our sigma max. This is the limitable or permissible stress. Now see here, this now we are going to find out the bending stress and direct stress. Because here this load is, if the load is acting here, only tensile, but the load is offsetted from 150 mm from the axis of the beam. Horizontal section, I mean, horizontal section of the axis of the beam is 150 mm offsetted from the load, and also the load is, I mean, in acting at a particular angle of the on the cross section of the beam. Hence, this load can be resolved into two components. One is vertical force component, another one is horizontal force component. Then we have to find out vertical force component and horizontal force component. The vertical force, horizontal force component, I mean, it's nothing but sine 30. I mean, sine 30 into P. Sine 30 into P. Okay. And vertical force component, I mean, P into sine cos 30, cos 60. Sorry, this is sine 60. You may consider, you have to cos, sorry, sine 60. I already told that sine 30, sorry. This is a PH, horizontal force. I mean, with respect to this diagram, you can easily find out the two vertical, two components of the force. One is vertical, another one is horizontal. That's what we are finding here. I mean, the horizontal force component is 4,310, 4,330 Newton, and the vertical force component is 2,500 Newton. Now, find the bending moment in the cross section. I mean, find the bending moment in the cross section. I mean, we know horizontal force, vertical distance. I mean, 1 pH into 150. pH into 150, horizontal force into vertical distance, right? And plus vertical force into horizontal distance. Vertical force into horizontal distance, PV is nothing but 2,500 into 300. We know that, right? Because here 300 distance. Then, I mean, this is our total bending moment. Now, our region of interest here, I mean, our region of interest they mentioned in the near the fixed end. Hence, I am considering 300 mm. But here, just given the cross-section area only here, they marked it out. Okay. Hence, now find out the bending moment. Then the total bending moment is going to be, I mean, 1,399 into 10 power 3 Newton millimeter. Now, this is the bending stress. What is the bending stress? Sigma B is equal to sigma mb by y. Then find out the bending stress in terms of T. Because they didn't give the dimensions of the cross section, then finally we are finding in terms of T only. Okay, because they have given all the dimensions, cross section of the bracket, they have given, I mean, in terms of T. Then finally we are finding in terms of T only. Now, what is this bending moment? I mean, sorry, this bracket now subjected to direct tensile load. When the force is acting, this is going to be subjected to tensile load. Then find out the tensile load. Tensile load, which force I have to consider for tensile load? Please tell me that, PH or PV, for finding the tensile load. Yeah, please, someone, please reflect. While the beam subjected to tensile, which load we should consider for finding the tensile stress? PH or PV?
PH.
Yeah, exactly, pH. So because axis is parallel to the pH, then pH by A, the A also going to be given 2T into T, then this also going to be in terms of T. T. Now calculate the, now we are going to calculate the cross section of the bracket. Now here this is the bending, this is a tensile. Then superimposing concept, apply the superimposing concept, both sigma for finding sigma max, then sigma B plus sigma T. Then finally, this is both component to be in terms of T. Then, I mean, then finally our rule is restrict with our permissible stress. I mean, this component equal to allow permissible stress must be equal to permissible stress for safe design. Hence, finally, we are finding this third order polynomial equation, T cube minus 37.89 T minus 36,740 roughly. Then solve this equation, then you are going to get 33.6 mm, then we can consider 35 mm. Once this is a thickness is finding, then the depth of the bracket is 2 into T, then 70 mm. Okay, the 2 into T, then it will be 70 mm. Yeah, please, if you have a doubt, please ask me that. This all problems are simple problems only. Okay. Even I have given some problems here. I mean, you have to solve it. And if you have any doubt, please ask me that. That's what I already shared you the slides. In this problem, if you have any doubt, please ask me. Okay. I come to next problem. How many students are there? Yeah, Kalyan, are you there in the meeting?
Yes, sir.
Yeah, only 50 students are there. Total 80, na?
Today 4 p.m. we have one OT, sir. 4 p.m.
What is that? What is that? I'm not getting.
Today we have OT, sir, at 4 p.m. Some students have OT.
Okay, okay. Please attend all the students. Please ask them to attend the class, all the students. Okay.
Okay.
Yeah. And now I come to this next problem. I mean, each problem's very important. Okay. So now see here, this problem is there are acting tensile load, direct tensile load, direct bending load. Okay, and the torsion moment. Okay, see here, the shaft is subjected to bending load 3 kilonewton and pure torsion moment torque 1000 Newton meter, and the pulling force, it's nothing but a tensile load 15 kilonewton. I mean, all three types of load is playing here. I mean, sorry, different types of load is playing here. Okay, now see this some interesting sum. Now they have given this load, I mean bending load 3 Newton, 3 kilonewton, torque is 1000 Newton meter, and P is equal to, I mean direct tensile load is 15 kilonewton. Means please, whatever the sum they have given Newton meter, try to convert based on your component dimension. Here they have given Newton meter. The component dimension they have given 15 mm. Hence, you'd like to convert into mm. So 10,000 into 10 power 3 Newton millimeter. Because most of the students are doing mistake here. Okay. We identified in the last semester also when I taught DT. Okay. Now the cross section is very simple. I mean pi by 4 d square, you can get it. And what is the direct stress? What the direct stress, you can find it out. P by A. I mean 7.64 m megapascal. Okay. Our aim is to find out the stress at A, stress at B. Okay. Now, before finding stress, before going to a stress at A, stress at B, we have to consider all the components to find out the stresses. What are the stresses are acting in this component? Okay. Now, the bending moment. What is the bending moment? It's very. This looks like simple cantilever beam. Bending moment is 3 kilonewton, 3000 into 250 mm. Then I mean 750 into 10 power 3 Newton millimeter. This is our bending moment. Okay. Now based on bending moment, we can find out the bending stress. See here. Yeah, 1 minute. These letters are, is it visible? Sorry. Is it okay now?
Yes, sir. Now it's fine.
Yeah. Now see here. I mean, whatever we discussed earlier. I mean, this page or the earlier page. Yeah, this only. Yeah. Yes, I mean, this is Z is nothing but our MB by Z, no, nothing but a section modulus. Sigma B, where is my pencil? I can't access in this. I can't access my pen, I think so. 1 minute. I open my pen, then. Sorry. Okay, I tell you directly. See here. I mean, here sigma B is equal to m by I into y. That y they are taking to denominator I by y. I by y is nothing but our section modulus. Section modulus I is equal to nothing but pi by 64 d power 4. Y is nothing but d by 2. Then you can find it out is z. Okay, that's what they put it here. Sigma B is equal to m by z. Then bending stress we know now. Once we find out the bending stress, we know that component, which portion going to be a compressive, which portion going to be a tensile, like that, right? Now the point A, see here, the point A here going to be subjected into compressive or tensile?
Tensile.
Tensile, sir.
I mean, at the point B, it will be compressive.
Compressive, sir.
I mean, compressive. Now, see here, now based on that, we can easily find out the stress, how much stress is acting in the point A. The resultant stress at the point A, I am going to add, direct tensile stress plus our bending stress. Direct tensile stress is 7.64 megapascal. Our bending stress is 61.1 megapascal. Then this is a total stress acting at the point A in the beam at near the fixed region, fixed position. Okay. Now resultant stress at the point B, it's a compressive stress. I can consider either this sigma B I may consider negative or sigma not sigma, direct stress I may consider negative. But I'm mentioning here compressive stress. Hence the sign is doesn't matter. Okay, that's what I'm considering. Any one of the stress I'm considering as a negative. So 61.1 minus 7.64, 53.46 megapascal. At a point B, the beam subjected into 53.46 megapascal. Now, we know that the shear stress, because the shear stress at the point A and B due to the torque also acting, right? Here, torque also subjected to beam, the torque also subjected into the beam, 1000 Newton meter. Then we would like to find out how much is shear also. Okay. Now that's what. Now the torque. See here. This is came from this formula T by J. 1 minute. T by J G theta by L tau by R. These two relation, you take it, you can get it this formula. Tau is equal to 16 T by pi d cube. This is polar moment of inertia J. T tau by R. Sorry, this R is not this R. Sorry. Extremely sorry. It should be a small R. This is a, if you put that R, that is a bending moment. During deflection of the beam, that radius of the beam. This is the R, tau by R. Okay. Now, see from these relations, I can find it out. What is the shear stress acting in the point A and B? It's a 40.74 megapascal. Now, I stress at the point A. Now, shear also subjected, right? Now, how many components are presented now? Two components, shear, sigma, and tau are presented in the component now. Then we have to go for principal stress theory concept. Well, when tau and sigma is playing, we have to go for the principal stress concept theory to find out the maximum principal stress and minimum principal stress. Hence we are coming to that concept. Because earlier we didn't find the shear stress. Only we dealt with normal stress. Now we are dealing with the shear stress. Hence, we are going to use this principal stress theory concept for finding the maximum principal stress and minimum principal stress corresponding to point A and B. Now see here sigma A by here only one stress is there. We are considering at a point A. At a point A, only one stress is there, sigma A. You may ask that where is sigma X, sigma Y? Only one normal stress. We are not considering sigma Y here. Please don't worry that. Okay, we already find it out at point A. This is a stress component. Okay, now I'm using that sigma X minus sigma Y. Sigma Y is not there. Only I'm considering any one. Then sigma A I'm considering sigma A divided by 2 plus 1 by 2 whole square root of sigma A squared plus 4 tau square. This is the sigma maximum principal stress. Okay, now finally this 87.67 tensile maximum principal stress at the point A here. At the point A here. Now, similarly, what is the minimum principal stress at the point A? Use minus sign and you are going to get minimum principal stress is 18.93 megapascal. Okay, now we have to find out maximum shear stress. Once you find out sigma max and sigma mean, sigma 1, sigma 2, we are able to find out what is the maximum shear stress at tau 1, 2. Okay, now this is our tau 1, 2, 53 megapascal. Tau 1, 3 is 53 megapascal. Okay. See here, one more thing. I mean, we didn't change the sign here. Whatever sign we used is compressive. Directly you have taken that. Then here also we are putting compressive. Then don't put sigma 1 minus sigma 2 divided by 2. Here already compressive nature. Then when you are going this formula also you can apply, or else you can apply this formula also. I mean, just directly put it here. 83 plus, I mean, this is already in compressive minus sign. Here sigma 1 is already in plus sign. Sigma 1 minus sigma 2. I mean, minus sigma 2, it will become a plus 18.93. 87 plus 18. Then it will be a 18, right? 80, okay, you can consider 19 here. You can consider 88. Then 88 minus 19, but here my already compressive, hence I am putting sign minus into minus plus. The 88 plus 19, 107, then find divided by 2, finally you are going to get 53.3 megapascal. That way also you can find it out. Now we know that the sex of mine at the point B. Now we come to the point B now. Okay. Now the point B, sigma B by 2. Same concept you apply here. Your point B, you are considering now 53.46 megapascal. This one. Okay. Point B. Now see here, and now this is our max point B. Always point B is always compressive, right? See here, point B is always compressive. Hence, I am using compressive. Sigma 1 at a point B, compressive. Minimum principal at stress at a point B. I mean here again I am using minimum principal stress. Again it will be a tensile. Here it is coming tensile. Okay, and similarly you can find it out at tau at a point B. Tau at a point B. This. So very careful when you are dealing with the sigma and tau. We have to use the principal stress theory concept for finding the, I mean, sigma 1 and sigma 2 this place, as well as tau 1 2. I mean, tau 1 2 means here no direction, no plane. For our understanding, I am putting here because here tau max. That's what they didn't use tau 1 2 like that. This sigma max, sigma mean. What is this point? Sigma max, sigma mean. We would like to find out. That is our intention. That is our aim. Okay, that's what we are finding the principal stress, maximum principal stress corresponding point A and B, minimum principal stress corresponding point A and B, and tau max corresponding A and B would like to find out. Now I come to this problem. Okay, see this is very interesting problem. Please, what is time now? Hey, what is time now?
3:55.
Okay, 3. Okay, we try to finish. Next class we are going to discuss further more problems from other books. This also I have taken as some problems from other book only. We would like to discuss some more problems. That's what my intention. Okay, now see here. I mean, the load on a bolt consists an axial pull of 10 kilonewton. Just imagine it. Whatever we discussed earlier problem, not nut and bolt problem, that is a different. Only we consider that how much extension, how much contraction. But now we are going to designing the nut and bolt. Okay, in that designing the nut and bolt, how these theories are playing. I mean, theories of failure concept, how it is playing, we are going to discuss now in this problem. Okay, now the load on a bolt the load on a bolt consists of an axial pull of 10 kilonewton together with the transverse shear force 5 kilonewton. When you are tightening the nut, you are applying the shear force 5 kilonewton. Okay, I mean this is, and our aim is to find out the diameter of the bolt required. I mean, based on maximum principal theory, maximum shear stress theory, maximum principal strain theory, and the maximum strain energy theory, and maximum distortion energy theory. This all 5 theories we are going to apply and find out the dimensions of the bolt, which one is suitable dimension. Okay, based on this theories, we are going to find it out. Now the permissible tensile stress is already given. I mean, 100 megapascal, and Poisson resistance is given 0.3. Okay, now come to this direct problem. See here, I mean, this is a 10 kilonewton. They have given axial pull. This is a tensile, right? And 5 kilonewton going to be in shear. This is a shear. This is tensile. Okay, now diameter of the bolt D, cross section of the bolt, by 4 D squared. I mean, due to axial force, I mean, we can find out direct tensile is P sigma 1 is equal to P PT by A. Then we can find it out 12.73 in terms of diameter square. That because our aim is to find out diameter of the bolt. Okay. Now come to the shear stress. Shear stress also given, right? Shear load is given 5 kilonewton divided by area, cross section area. Then 6.365 divided by D squared into D squared kilonewton per mm squared in terms of D. Shear stress given. Shear we have found it is we have found that shear stress. We have found that normal stress. Then I mean obviously we are going to play with the maximum principal stress theory. I mean now they have given clearly maximum principal stress theory. Suppose if they are not given, we have to go for like earlier problem. Okay. Here they have given clearly maximum principles, follow the maximum principal stress theory and other theories, then find out the diameter of the bolt. That's what they're directly given. Now see here, I mean, this is sigma T1. It's nothing but the maximum principal stress, and sigma 1 plus sigma 2 divided by 2. Here sigma 2 is not there. Here sigma 2 is 0. I mean, here this is plus 1 by 2 square root of sigma 1 minus sigma 2 whole square plus 4 tau square. Please don't worry about this sigma 1, sigma 2. This is nothing but sigma x, sigma y. Sigma x, sigma y. This sigma 1, sigma 2, don't think principal stress, please. Okay, this sigma x, sigma y. This is tau xy. Okay, like that you have to consider, assume that, otherwise it will be confused. Okay, then this sigma 2 I am considering 0. It's now nothing but sigma y. Now sigma 1 by 2 plus square root of sigma 1 square plus 4 tau square. Substitute these two values. I mean sigma 1 and the tau value. Finally, you are going to get mean the maximum principal stress you are going to get in terms of D squared, 15,360 divided 65 divided by D squared. Now maximum principal theory, we know, right? Now what is the condition they have given? Now the condition is, I mean, the elastic limit is, I mean, permissible elastic limit is 100 megapascal. Then I am comparing with my 100 megapascal because already give this is our stress. Our stress must be compared with the permissible limit of stress. Then permissible limit is 100 megapascal. Then I able to find out diameter of the shaft, diameter of the bolt. Okay. Now, when you are coming to according to maximum principal stress theory, maximum shear stress theory, second case, sorry, maximum shear stress theory. Now we are considering tau max. Tau max is nothing but sigma 2.
Hello, sir.
Hello, sir.
Sir left the meeting.
Hello, are you able to hear?
Yes, sir. Audible.
Yes, sir.
Yes, sir.
Yes, sorry, here power shutdown. We are having last 3 days continuous raining here. I mean, just now I connected my mobile network. Yeah, please just we complete this problem, then we leave the class. Please cooperate. The next class we discuss for a few more problems because only we complete this problem. Okay. As in, is it recording or not? Please, someone reflect because I'm in
Sir,
presentation.
it's still
It is
recording.
recording, sir.
Okay. Yeah, come to this. Yeah, up to this we discussed, right? Where is my pointer? Just 1 minute. Where is torchlight? Torchlight. Dark light. Okay, 5 minutes on the torchlight. Yeah, sorry guys. See, this is second. We are going to consider the maximum shear stress theory. I mean, same
Sir, you're
concept.
not presenting your screen, sir.
Oh, okay. Sorry. Okay, now, are you able to see?
Yes, sir.
Yes, sir.
Thank you. Now the second theory we are going to follow to define our diameter of the bolt based on maximum shear stress theory. I mean, tau max is equal to 1/2 square root of this equation. We are very well known, right? Then so I directly substitute this sigma 1 value, whatever we found it earlier. I mean, 12.73, where it is here. Yeah. Yes. 12.73 here. Whatever we find earlier, 12.73. You can see my cursor. 12.73 by d squared sigma 1. Tau is given 6.365 d by d squared. The value substitute here, you are going to get tau max. I mean, tau max, once you get it tau max, I mean, right, our permissible limit tau max is, I mean, already here given 100 is sigma yt or syt based on maximum shear stress theory. What is our tau max limit? How can I find it out? Based on the diagram, whatever we discussed, the hexagon diagram here, 0.5 syt from the hexagon diagram, what we discussed in the maximum shear stress theory, 0.5 syt or sigma yt. Hence, I'm using here 0.5 syt divided by 2. 0.5 SIT divided by 2. I mean, already sigma YT given. Sigma YT in terms of permissible stress they have given divided by 2. I mean, suppose here they given, this is not permissible stress, directly given SYT. Then what we will do? SYT may be 200. Then we have to find it out. SYT divided by factor of safety. Then that will become a permissible limit. Then that will be multiplied by 0.5. Very important. That will be multiplied by 0.5. Okay. Hence, here I am considering 100. Already this is given in terms of permissible tensile stress. Hence, I am directly multiplying 100 into 0.5 based on my theory, based on my maximum shear stress theory concept, from which one we learned from the diagram. Now, you can equate this. You can find it out the diameter of the bolt 13 mm. Earlier case diameter of the bolt 12.4 mm. Okay. Now the next. Okay, I complete this page. Then we stop our today's discussion. Please cooperate. Just for 2 minutes. I mean, the next theory, according to maximum principal strain theory, right? Again, we have to find it out sigma 1. Sigma 1 and sigma 1 we know, and the minimum principal stress we know. We already discussed the maximum principal stress. Now we are considering minimum principal stress, because the earlier case here, yes, everything we discussed already here. 15,365 divided by d square, Same value you are getting here. Okay, no problem. Now this is our minimum maximum principal sign theory. We need both value, sigma 1 maximum principal stress and minimum principal stress. When you are up, substitute the values whatever we obtained, sigma 1 and tau value, finally we are going to get the maximum principal stress and maximum principal stress in terms of D and D squared, and minimum principal stress in terms of D squared in negative sign. Then you apply the concept maximum principal stress theory, strain theory, maximum principal strain theory we discussed earlier in the formula. In the beginning of the class, sigma RT dot by E minus 1 by M into sigma 2 divided by E. Wherever we are playing with the strain energy theory, the Poisson ratio concept must be there, Poisson ratio effect. Hence, we are using 1 by M. Hence, see here in this theory, now you substitute the values. Now you substitute the values. This must be, the left-hand side is our component design. Sigma 1 minus by E minus sigma 2 divided by E into mu is equal to, strain energy theory, right? Strain energy is nothing but, sigma by E, strain, right? Sigma by E, see here, sigma by E. Then both side will be, E will be cancelled out. And we know this left-hand side value we already know. 15,365 divided by D square, minus it will be a plus sign, 2,635 by D square, into Poisson ratio is given 0.3, then right-hand side going to be 100. Then you can find it, the diameter of the bolt is 12.7 mm. Now I come to according to the strain energy theory. The strain energy theory, the same concept you apply here. We already evaluated sigma 1, sigma 2 values. Directly substitute this theory. This is the theory. This is sigma 1 squared plus sigma 2 squared minus 2 sigma 1, sigma 2 divided into mu. Into mu, the right hand side is going to be a standard test specimen value. This is nothing but now it will be our permissible stress value, because this thing now already divided by factor of safety. Now the left hand side is now our component designed value. Then you can find it out diameter from this relation. You can find out the diameter of the bolt. 12.878 mm. Now I come to the last theory according to maximum distortion energy theory. See here, these two formula almost same. Only you have to remove M. Mu should not come, because here maximum distortion energy theory we have already discussed, sigma 1 squared plus sigma 2 squared minus 2 sigma 1 sigma 2 is equal to, right hand side is standard stress specimen value is given now in the form of permissible stress value. Now already we know all the values, sigma 1 sigma 2, plug into this equation, you are able to find out the diameter of the bolt. Okay, 13.4 mm. So now I stop here. Now which diameter is suitable diameter? 13.4 is suitable or 12.4 is suitable?
13.4.
Yeah, thank you. See, you see here the maximum shear stress theory and maximum distortion energy theory almost giving same value. Even that maximum shear stress theory and distortion energy theory, we have observed that that hexagon region and the cubic curve almost close to each other in the quadrant of third quadrant and fourth quadrant. Okay, hence these two value we may consider. 13.4 or 13.4, what is that value? 13.42. Then we can consider approximately 14 or 15. Okay, 14. That also we will discuss in the next subject. I think. Suppose they have given the table. DT, when the people study the DT, design of transmission elements, they can consider round figure value 13.42. They may consider either 16 mm or 18 mm like that based on design data book. Okay, now we can consider 13.4 mm. Okay, thank you guys. Due to power shutdown, I delayed a lot, 2, 3, 5 minutes. Sorry for that. I stop it here. If you have any questions, please go ahead. The remaining thing we will discuss. I mean, there are very important problems, these two problems, and for some more problems, I bring it in the next class from other books, okay? And we will discuss in the next class. Then we are going to start next class, our third chapter. Yeah, please go ahead. If you have any doubts, please go ahead. I first come to chat box. Is there any questions? Okay. Thank you, Amarnath Biswal. Thank you, Karthik. Thank you, guys. Any questions, please?